Hi, let's begin by solving the question number 4 for our NSEM solutions. We shall start with part A. Explain any four common feature engineering techniques for continuous or categorical data. So let's start with that. Um, Feature engineering is the process of transforming raw data into meaningful input that enhances model performance no matter how powerful an algorithm is. Its effectiveness depends on quality of the feature supplied to it. In practice, feature engineering can reduce noise, can reveal underlying structure, can stabilize the model behavior and improve the generalization of predictive models. So one technique for continuous variables in normalization is uh, one technique for continuous variables is normalization or standardization. These techniques rescale the data. Normalization typically maps the values between 0 and 1. Standardization, in contrast, recenters the data to have 0 mean or unit variance. These transformations are particularly important for algorithms that are sensitive to feature magnitude and such as like gradient descent or optimization based or distance based models. As an example, the salary versus the age group can overshadow the outcome of the model since in case we are using the distance based model or gradient descent model because the features are too overpowering for it. Another technique is the binning or discretization. Um, Here we take the continuous variables and convert it into a set of categorical bins. For example, if we have the age variables, which we may convert into such ranges such as 0 to 18, 19 to 35, 36 to 60, and 60 plus, and so on and so forth. This simplifies complex distribution and reduces the effect of outliers and helps certain models capture nonlinear relationships. Another technique is one-hot encoding. One-hot encoding is widely used in categorical variables rather than assigning a single um, numeric label to each category. We can incorrectly imply an ordered relationship. We can create binary indicator variable for each category. This helps maintain the categorical nature of the features and prevent the model from learning invalid numerical relationships. After that, we also have target encoding, which is another approach which basically we replace each category with the average value of the target for samples belonging to that category. This approach is especially useful in high cardinality features and is commonly used in tree-based models like forest tree, decision tree. And however, it must be applied carefully to avoid target leakage and typically through cross-validation techniques. So let's proceed to the next subpart of the question. What is sampling for a distribution? Describe inverse transform sampling or Monte Carlo sampling with an example. So let's do that. Uh, Sampling from a probability distribution refers to generating random values that statistically follow the shape of the distribution. Uh, Basically, this is the fundamentals in simulation and probabilistic modeling and Monte Carlo techniques. Rather than computing an integral analytically, which may be difficult or sometimes impossible, we approximate the expectation using a random draws of the distribution. Inverse transformation sampling is a general method of for sampling um, from any distribution function, cumulative distribution function, CDF is known. The method is straightforward. We begin by sampling a uniform random number between 1 and 0. We then apply the inverse of the CDF to that number. The result is a random sample that follows the original distribution. For the example of inverse transform sampling, let's consider the exponential distribution with rate lambda. The CDF is 1 minus e to the negative lambda times x, and we can then invert this expression. We obtain x equal to negative 1 over lambda times the natural logarithm of 1 minus u. So if we draw the uniform random value of zero point 0.3, we can plug this into the inverse CDF function and obtain a sample from the exponential distribution. Now let's talk about Monte Carlo sampling. So in Monte Carlo sampling, we repeatedly draw random values and use those values to basically approximate the quantities of interest. A classic example is the estimating the value of pi by randomly scattering points inside a unit square and determining the proportions that fall inside the inscribed quarter circle. As the number of samples increase, the approximation becomes increasingly more accurate. So this would be it for the fourth question. We shall solve the next question in the next video. Thank you.